This is Team 12, Apex Engineering Group with the San Diego State University New Student Residency Hall site preparation. My name is Alexis Dial. I'm the project manager for my team, and I will be walking you through this process and introducing you to my team as we progress through this presentation. The main scope of work for this site preparation was geotechnical analysis, foundation design, and retaining wall design. The scope of work also included earthwork calculations, a cost analysis, and a construction schedule. The geotechnical analysis will be explained by our geotechnical lead, Jared Ramsey.
The first part of the geotechnical analysis was the review of provided boring and test pit samples from Group Delta to determine the soil conditions. A series of cross-sections were made from the site layout with the location of the boring and test pit samples. Using these cross-sections, profiles were created showing soil conditions under the proposed foundation location. ASTM Standard D2487 charts and nomenclatures were used to classify the soil and understand the strength and potential for loading. Profile A had a large Eocene layer of poorly graded cobble conglomerate. The soil in the middle of the site is shown in Profile B. This profile in particular had layers of soil, such as sandy fat clay, that alone could not support a large load. Profile C ran along the east side of the property and also contained a large layer of the poorly graded cobble conglomerate. Linear interpolation was then used to join these profiles into a 3D representation of the site. After reviewing the soil, many of the layers had either high plasticity or low density as defined by the standard penetration tests, or were fill soils from the existing parking lot. None of these soils could support a traditional shallow foundation, especially for the size of the proposed 6-story building. The usable soil underneath was the Eocene layers of clay, sandstone, or cobble conglomerate. Both of these layers are very dense, with standard penetration test N60 values from 90 to 120. These dense soils have the bearing capacity for end-bearing piles, as well as providing skin friction for the shafts. Due to the fact that these layers started at 15 feet below the surface or lower, a cast-in-place drilled hole pile foundation system was recommended. With these deep piles throughout the entire foundation, no soil needed to be removed, and the native soil was sufficient for the T-wall retaining wall system proposed by the structural engineers.
The earthwork calculations will be explained by the earthwork lead, Daniel Bagayo.
In order to complete site preparation and grading, we first had to estimate the square footage of the property. Then, in Civil 3D, we calculated the amount of soil to be moved by creating a surface to reference the existing elevation given in the topographical map. It was determined that approximately 4,700 cubic yards of cut were needed and 18,000 cubic yards of fill were needed. Therefore, to meet grade requirements, approximately 13,000 cubic yards of soil needed to be imported.
Before we selected a wall type, preliminary calculations were done. This section will be explained by Sydney Reyes.
For the SDSU Residence Hall project, a retaining wall is required in order to level out the ground due to the cliff located on the northern side of the property. To determine the best retaining wall selection, preliminary calculations were performed for a king post tieback, cast-in-place concrete cantilever, and an inverted T-wall. King post tieback walls are beneficial due to the fact construction is fast and quiet. However, fluctuating steel prices and difficulty in construction due to excavation hinder the king post tieback from being a feasible option. Cast-in-place concrete cantilever walls are genuinely beneficial since it has an economical height range and are commonly constructed throughout the country. Some disadvantages include lengthened construction and an access easement to account for the large size of the footing. The last option, an inverted T-wall, proved to be the most beneficial because of its cost competitiveness, minimal maintenance, built-in drainage, and easy construction. The only disadvantage found for this option is the need for a precasting site for the T-blocks.
Daniel will explain the final wall calculations necessary after the T-wall was selected as a retaining wall.
When considering loading for the T-wall, we had to consider a traffic surcharge, soil pressure and unit weight, and concrete self-weight. Since the T-wall is a proprietary system, the Neal Company has typical sections for each type of module. So rather than designing the steel and reinforcement for the wall, we used the typical module size and reinforcement and completed calculations to check factors of safety for overturning, sliding, and pullout. To determine the factor of safety for overturning, we first had to calculate the total resisting moments that the wall exhibited on the soil, and the overturning moments that the soil exhibited on the wall. Then the factor of safety was calculated by dividing the sum of the resisting moments by the sum of the overturning moments. Next, to determine the factor of safety for sliding, we had to calculate the sum of the horizontal driving forces and the sum of the horizontal resisting forces of the wall. Finally, to determine the factor of safety for pullout, we had to calculate the pullout resistance of the wall based on the weight of the concrete units, unit weight of the soil, friction angle of the soil, resistance factors, and the effective area of concrete behind the Rankine active zone. The factor of safety was determined by dividing the pullout resistance by the pullout force. Calculations for factors of safety were completed at each level of the wall.
The final step in the retaining wall portion of our project was the design. Our CAD specialist, Dane Walker, did the design for the T-wall.
The inverted T-wall system is placed on two 15-inch by 6-inch unreinforced concrete leveling pads. These pads lay the foundation for the inverted T-wall system. The leveling pads vary in depth according to the wall depth. Other initial construction requirements for the T-wall include the soil embedment. The face of the T-wall requires 2 feet of depth in the soil at all locations along the length of the wall. On this project, the face of the T-wall is being built 3 feet off of the property line right-of-way. The top parapet wall panels give 3 feet of clearance between the top of the panel stems to the final elevation of 426 feet. This clearance allows space for the topsoil and asphalt for the fire road. Another design feature of the wall is a half-inch spacing between the panels. This half-inch spacing is created by the neoprene pads placed between each panel. This allows for 2 crucial features: California seismic compliance and the drainage of water through the wall. Some other design considerations of the T-wall system includes parameters such as the backfill to not exceed 130 pounds per cubic foot, and the face of the T-wall can be architecturally treated to meet the needs of the client. Construction feasibility reduces cost of this wall compared to other wall alternatives, especially due to the fact that the wall is made to last and is completely maintenance-free for our SDSU client in the future.
Taryn Linderman was the lead for the foundation portion of the project. She will explain the calculations and design of the foundation.
A deep foundation was recommended from the geotechnical investigation due to poor quality soils and proximity of local fault lines. Having only been given one story of the building floor plan, it was decided to assume all stories the same and use projected column locations to determine pile locations. As pile reinforcement should extend directly into column reinforcement, most all piles were placed directly under column locations. As seen here, piles were placed all around the building pad perimeters. Spans between piles on the pads were not large enough to require additional piles to support building loads. As a result, the piles were placed as shown. Once pile locations were determined, pile loadings were calculated according to ASCE 716, live load recommendations, and assumed dead load and seismic load using the load paths. Once complete, the largest pile loading calculated was used as the ultimate pile capacity with a factor of safety of 2.5. Because all that was known at this point in time was the site soil data and the now calculated ultimate capacity of the piles, pile depth calculations were done backwards to determine their depth. All assumptions are listed here. Our initial diameter was 6 feet, and assuming all poor quality soils would hold no load, pile depths ranged from 54 to 61 feet deep. Cast-in drilled hole piles were chosen as the foundation type. Once the pile dimensions were determined, reinforcement was detailed. It was decided to use 9 number 10 steel bars as longitudinal reinforcement with 3-inch cover and number 3 tie bars at 18 inches center to center. The pile's design should be more than adequate to withstand the building loads for the new residence hall.
The cost portion of our project was led by Martin Barajas.
As we move on to the next slide, we see the project summary of costs for the net direct site cost. On the left side of the table, we see the elements, foundations, site preparation, and site improvement. The middle column is the total cost, and the third column is the cost per square foot of the area. The foundations include the foundation, piles, and the slab on grade. The site preparation includes the site demo, site prep, erosion control, and traffic control. And the site improvement includes the retaining wall system and the landscaping for the whole project. Moving on to the project summary of cost, the net direct site cost for the whole project is $1,417,442. This is roughly around $14.56 per square foot. After adding 15% for the general conditions and 5% for the escalation to midpoint of construction of January 2019, we will have a total base bid cost of $1,762,908. This is roughly around $18.11 per square foot of the area.
The construction schedule was designed by Martin Barajas, and he will briefly explain the schedule.
The schedule is broken into 4 phases. Phase 4 and 3, which is the northeast and west of the site, both include the retaining wall in their scope. Phase 2 and 1, the southeast and west of the site, both include the foundation in their scope. As we see down below, this was taken out of the schedule itself. The screenshot down below from Primavera P6 will give you a nice overview of how the phases were laid out throughout the duration of the project. The SDSU Residence Hall project will start on February 4th, 2019 and has an expected finish date of December 19, 2019. The project duration for the whole project, which includes the site prep foundation and retaining wall, is 10 months and 15 days. After analyzing the cost and schedule for the project, a few recommendations have been made. A T-wall system is 40% less expensive than traditional retaining wall systems due to a number of factors, such as the labor cost, material cost, and fewer activities on the schedule.
This concludes our presentation. Thank you for your time. For further information, follow the link at the bottom of the page for our full project.